Hey there, future AI masters. Imagine a world where computers can learn just like humans. Yep, just like how you learned to recognize apples and oranges as a kid. But what if I told you that you can teach a computer to do the same? Well, that's called supervised learning. By the end of this video, you'll know exactly how to build a supervised learning model step by step. Whether you're a kid, a student, or a professional, this adventure is for you. Let's jump into the world of AI together. Meet Sam and Lily. They are best friends with a big challenge ahead. Their town is opening a super AI bakery. But there's a problem. Customers are angry because bakers keep mistaking muffins for cupcakes. So, Sam and Lily decide to train an AI model to solve this problem. But how? With supervised learning. Think about how you learned to recognize cats and dogs. Your parents showed you a cat and said, "This is a cat." They showed you a dog and said, "This is a dog." After seeing enough examples, your brain learned to recognize them. Supervised learning works the same way. We show the AI examples labeled data, and it learns from them. So what is supervised learning? It's when we train an AI using labeled examples to make future predictions. Sam and Lily will teach their AI to recognize muffins and cupcakes using labeled images. Before we start building our AI model, we need to understand two types of supervised learning classification for categories. When we want to classify things into categories. Example, muffins versus cupcakes. Other examples, spam emails, detection, disease diagnosis, face recognition, regression for numbers. When we want to predict numbers based on data. Example, predicting cake prices based on their size. Other examples, stock market prediction, weather forecasting, salary estimation. Since Sam and Lily want to separate muffins from cupcakes, they will use classification. Now let's train our AI model step by step. Follow along. Step 1. Define the problem. Our goal is to train an AI to recognize muffins and cupcakes from images. Step 2. Collect and label data. Sam and Lily take 1,000 pictures of muffins and cupcakes from the bakery. They label each image correctly, for example, muffin or cupcake. Step 3. Prepare the data. We clean the images, remove blurry ones, and make sure they are properly labeled. Step 4. Split the data 80%, training data to teach the model 10%, validation data to fine-tune the model 10%, test data to evaluate the model. Step 5. Choose an algorithm for classification. They can use decision trees, random forest neural networks. Sam and Lily choose random forest because it's great for image classification. Step 6. Train the model. They use Python and scikit-learn to train the model on labeled images. Step 7. Test the model. They show the AI new images and check how well it predicts. Step 8. Optimize the model. If accuracy is low, they adjust parameters to improve performance. Step 9. Deploy the model. Finally, they integrate the AI into the bakery's self-checkout system. Now, it can automatically classify cupcakes and muffins. Now let's see how regression works. Imagine a cake shop wants to predict cake prices based on size. Regression example: input cake size in inches, output cake price. Using linear regression, they train the AI to predict the price of any cake size. Wow! Look at what we did today. We learned what supervised learning is. We explored classification and regression. We built a complete AI model step by step. We deployed a real-world application. Supervised learning is everywhere. From detecting diseases in hospitals to chatbots, AI is changing the world. And now, you know how to build one.
Supervised Learning Journey, a comprehensive technical guide to understanding, building, and applying. Supervised Learning Models. Supervised learning is a machine learning approach where models learn from labeled data. It involves mapping inputs to outputs using various algorithms. Understanding, theoretical foundations. Supervised learning consists of classification and regression. Key algorithms include decision trees, SVMs, and neural networks. Model performance is evaluated using metrics like accuracy, precision, recall, and RMSE. Building, model development process. Developing a supervised learning model involves data collection, pre-processing, feature selection, and choosing the right algorithm. Training includes hyperparameter tuning, and addressing overfitting or underfitting ensures better generalization. Applying, real-world implementation models can be deployed on the cloud, edge, or on-premise. They are widely used in finance, healthcare, and marketing. Continuous monitoring and ethical considerations help improve performance and mitigate biases. Title: What is supervised learning? Supervised learning is a machine learning technique where models are trained using labeled datasets. The algorithm learns by mapping input features, X, to corresponding output labels, Y. This approach enables the model to recognize patterns and make predictions based on past data. Supervised learning is widely used in real-world applications such as speech recognition, medical diagnosis, and fraud detection, making it a fundamental method in the field of artificial intelligence. Title: Core components of supervised learning. Supervised learning relies on three key characteristics that define its effectiveness. First, labeled data serves as the foundation, ensuring that every input has a corresponding correct output. Second, the training process involves iterative adjustments, allowing the model to minimize errors and improve accuracy. Finally, evaluation metrics such as accuracy, precision, recall, and root mean squared error, RMSE, are used to assess the model's performance. These core components collectively enable supervised learning models to make accurate predictions and generalize well to new data. Types of supervised learning: classification versus regression. Supervised learning can be broadly categorized into classification and regression tasks. Classification assigns labels to predefined categories, making it useful for applications like spam detection and disease classification. On the other hand, regression predicts continuous numerical values, which is essential for tasks such as stock price prediction and temperature forecasting. Both approaches play a crucial role in solving real-world problems and optimizing decision-making through data-driven insights. Understanding the problem statement. Defining the problem statement is a crucial first step in supervised learning. It is essential to clearly determine whether the objective is classification or regression. Understanding the business or research impact of the solution helps in aligning the model's purpose with real-world applications. Additionally, identifying the expected input features and output labels ensures that the data is properly structured for training, leading to more accurate and meaningful predictions. A well-defined problem statement sets the foundation for building an effective supervised learning model. Gathering and cleaning data. Data collection and preparation are essential steps in building a successful supervised learning model. Raw data is gathered from multiple sources, such as databases, APIs, and web scraping, to ensure a diverse and comprehensive dataset. Proper labeling of the data is crucial, as supervised learning relies on correctly mapped input-output pairs. The data is then cleaned by handling missing values, removing duplicates, and resolving inconsistencies to improve quality. Finally, feature engineering is performed to enhance input variables, ensuring the model can effectively learn patterns and make accurate predictions. Data splitting training, validation, and test split. To build an effective supervised learning model, the dataset is typically divided into three subsets: training, validation, and test sets. The training set, which constitutes about 70 to 80% of the data, is used to train the model by learning patterns from input features. The validation set, comprising 10 to 15% of the data, helps in tuning hyperparameters and preventing overfitting. Finally, the test set, also around 10 to 15% of the data, is used to evaluate the model's final performance on unseen data. This structured data splitting ensures that the model generalizes well and performs reliably in real-world applications. Data splitting training, validation, and test split. To build an effective supervised learning model, the dataset is typically divided into three subsets: training, validation, and test sets. The training set, which constitutes about 70 to 80% of the data, is used to train the model by learning patterns from input features. The validation set, comprising 10 to 15% of the data, helps in tuning hyperparameters and preventing overfitting. Finally, the test set, also around 10 to 15% of the data, is used to evaluate the model's final performance on unseen data. This structured data splitting ensures that the model generalizes well and performs reliably in real-world applications. Selecting the best model. Choosing the right algorithm is a critical step in supervised learning, as it directly impacts model performance and efficiency. For classification tasks, popular algorithms include logistic regression, decision trees, random forest, support vector machines, SVM, and neural networks. On the other hand, regression tasks can be tackled using linear regression, polynomial regression, ridge regression, random forest regression, and neural networks. The selection of an algorithm should be based on factors such as computational efficiency, data complexity, and scalability. A well-chosen model ensures accurate predictions while maintaining optimal performance for real-world applications. Building the machine learning model. Training a machine learning model involves using powerful frameworks like scikit-learn, TensorFlow, and PyTorch to implement algorithms efficiently. The model learns patterns from data through optimization techniques such as gradient descent, which helps minimize errors and improve accuracy. Throughout the training process, monitoring the reduction of the loss function is essential to ensure the model is learning effectively. Proper training techniques enhance the model's ability to generalize well to new data and make accurate predictions. Assessing model performance. Evaluating a machine learning model's performance is crucial to ensure its reliability and effectiveness. For classification tasks, key metrics include accuracy, precision, recall, F1 score, and ROS-AUC, which help assess how well the model distinguishes between different categories. In regression tasks, performance is measured using mean absolute error, MAE, root mean squared error, RMSE, and the R-squared score, which indicate how closely the predictions align with actual values. Additionally, cross-validation is performed to ensure the model's robustness and generalizability across different datasets. A thorough assessment helps refine the model and improve its predictive capabilities. Where optimizing model performance. Hyperparameter tuning is essential for improving a machine learning model's performance and efficiency. Various techniques are used to find the optimal parameters. Grid search systematically explores all possible parameter combinations to identify the best configuration. Random search selects random combinations, offering a more efficient alternative when dealing with large parameter spaces. Bayesian optimization takes a probabilistic approach, using past evaluations to guide the search for the best parameters. By selecting the right tuning strategy, models can achieve better accuracy, generalization, and overall effectiveness in real-world applications. Making the model production-ready. Deploying a machine learning model involves converting the trained model into a functional API using frameworks like Flask, FastAPI, or TensorFlow serving. Once packaged, the model can be deployed on cloud platforms such as AWS, Google Cloud, or Azure to ensure scalability and accessibility. Continuous monitoring of real-world performance is essential to detect any performance degradation, allowing for timely updates and improvements. Effective deployment ensures that the model remains reliable, efficient, and capable of delivering accurate predictions in practical applications. Where is supervised learning used? Supervised learning plays a crucial role in various real-world applications across multiple industries. In healthcare, it is used for disease detection and medical diagnosis, helping doctors make accurate predictions based on patient data. In the finance sector, supervised learning is essential for credit scoring and fraud detection, ensuring secure transactions and risk assessment. Retail businesses leverage it for customer segmentation and personalized recommendation systems to enhance user experience. Additionally, in autonomous vehicles, supervised learning aids in object detection and lane tracking, enabling safer and more efficient self-driving technology. These applications showcase the wide-ranging impact of supervised learning in modern technology. Common pitfalls and how to avoid them. Supervised learning comes with several challenges, but best practices can help mitigate these issues. Overfitting occurs when a model learns noise instead of patterns, which can be prevented using regularization techniques and cross-validation. Data bias can lead to unfair or inaccurate predictions, making it essential to ensure datasets are diverse and well-balanced. Scalability issues arise when handling large datasets. but leveraging cloud computing and parallel processing can enhance performance. By addressing these challenges effectively, supervised learning models can remain accurate, efficient, and applicable to real-world scenarios.